All right, let's get this started. Today we're doing 12.1. And if I'm feeling jiggy with it, we're gonna look at 12.2, but I doubt it.
We thought 3 weeks left.
Oh,
So that 6 classes. One for the project.
12.1 is the goodness of fit test. Somebody's in Hansel aren't doing their job, I see. They're sitting in the front row, their job, it's just one job you gotta do. I don't wanna hear excuses about how I'm too tired to fucking pull down the monitor. Chapter 12 in general, chapter 12 and 13 are on 3 or more sample groups. Look at the girls being more disruptive than the boys back there. You guys are troublemakers.
We didn't notice it started, that's why I was like, stop.
So involved with each other. They didn't even notice I've been talking for like a minute and a half.
We're talking about homework, actually.
Yeah.
Sure, that's what the boys are talking about too back there.
Oh,
All right, so the goodness of fit test. In this area, we're looking at, we've got a bunch of groups. And the goodness of fit test is like the idea of doing proportion testing for more than 2 groups. Now, at this point, we got 3 or more, and we can't just like say, we can't do that subtraction thing like we've been doing in the other ones. When we had 2 groups, we were able to say like the difference between them. We can't do that now that there's 3. So what we do is the idea here is that each sample has an expected proportion. Which may or may not match the other groups. Be the same as other groups. This blue pin is dead. I will dump it in a second. Hands on catch. Is that what you call it, teaching? I'll remember that shit. I was joking. Up here talking shit, point blank. Point blank.
I did miss.
So then then obviously we have to gather data. Data is gathered. And we test each proportion. And we test to see if the observed values match the expected values. And we don't do it on a 1-for-1 basis, we just do like the overall group. So the question we're asking is how well does the data fit our expectations? If I could spell out expectations, this would be a glorious day. There we go. And there's another quotation mark down there. Guess what I still haven't watched, Hansel?
Oh, Judge.
I don't even know what the fuck name is.
Jesus Christ.
Whatever the hell you asked me to watch, I didn't watch it. You
I
know,
sent them to you twice. Twice.
what do they say? Third time's the charm?
Glad to know that.
Says like that.
All right, so. So what are the requirements for this test? This is gonna sound funny because I didn't give you the statement I wanted to say before it. All expected values must be greater than or equal to 1. And if, you know, we're talking about proportions, that should sound silly. Because they're all less than 1. And then that's the first requirement, or option A, but or required, not option, but requirement A. Requirement B is no more than 20% of them are less than or equal to 5. Let me add more to that. No more than 20% of the expected values. Are less than or equal to 5. Find the expected values for each group. N times PI. Each group has its own proportion, so you're going to have a different expected value for each group. So way to kind of remember this, how well does the data fit our expectation? How good is the fit? That's where they come up with the name goodness of fit. Unfortunately, in StatCrunch, it starts there. Let's see, in SC, you have stats. It should go to goodness of fit. Then we're going to click on chi-square test. Looks like the green pin's dead too. I got a whole set of brand new, you know what? Fuck all those old markers. Let's just use all brand new pins. You guys deserve brand new pins. Except Hansel. He made fun of my teaching. You guys ready? Just making sure. Some of you used to write slower, now you got quicker. That's good stuff. All right, so Remember, we're doing hypothesis tests. We have 5 steps. So the thing that changes is the first step. So what is step 1 for this category? We need to know what H naught and HA are for the goodness of fit test. H naught is the observed values match the expected. HA is at least one group does not match the expected values. Okay, so that changes in this test. How we put it in StatCrunch, let's go back to talking about that again. Again, it's stats, goodness of fit. And then chi-square test. The symbol for chi is that. It's pronounced chi like I.
I thought it was pronounced cheat.
It looks like chi.
That was Kai.
I was trying.
Looks like chai also, doesn't it? Because like Chicago, it should have a ship. Chicago starts with CHI, but chick. It's not, it's a K sound. It's a chi. Like, no, fuck chi like that. It's like Cobra Kai.
Oh, right back.
If you haven't seen Cobra Kai, you'd be missing some good shit. Yeah. In StatCrunch, what we're gonna do is we're gonna enter you have to enter the data. So we have to enter the data. The values in column 1. Put the observed values. You're gonna have 2 options for this. Option A. Enter the expected values. This is where you're going to take the N and you're going to multiply it by each of the P individual PIs. You only have to do that if the P's are different though. If all the P's are the same, you like everything has the same proportion, like if you're rolling a die, every side should come up the same number of times. If all the P's are the same, you can bypass that step and just check mark cells are in equal proportion. Let's see. For how? Interestingly enough, this chi-square test does a chi-square distribution. It's not a normal bell curve. It doesn't do the normal bell shape, but I'll show you a picture of what it looks like. That became ugly. I don't want to redraw this, so I'm just going to put it up here real quick. So DF is n-1. So however many samples you have changes the shape of it. But like for DF equals 5, it's like really high up on the left, and then it's got a really long tail on the right. They all have really long tails on the right. How is that going to change what you're going to do here? Not changing it at all. So, just showing you the pretty graphs there. Let's look at an example. You guys ready for a great example? M&Ms. I feel like I fucking cheated you guys out of the M&M experience. The M&M or Mars Company produces M&Ms. And states that the distribution of color by color is what? Yeah, because even this program likes to use M&Ms. You distracted me. Shame on you. Brown, yellow, red. I've got blue, orange, and green. And they say the proportions are this: 0.13, 0.14, 0.13, 0.24, 0.20, and 0.16. This might be similar to question number 1, because I have a hard time thinking I had exactly 600 feet samples. So we tested 600 groups. And so, not groups, we got 600 M&Ms, opened up bags to have 600 M&Ms. And so we're gonna have an expected value of n times p is 600 times 0.13, 600 times 0.14, 600 times 0.13, 600 times 0.24, 600 times 0.20, And 600 times 0.16. When you multiply this all out. He's up here in my way. Some shit you did, I'm sure of it. And handle it disrupted my workspace. Now, our observed values are thus. We had 83 brown, 87 yellow, 70 red, 130 blue, 134 orange, and 96 green.
Is the 600 just like a random number?
Yeah. It was 600 M&Ms that we had.
Okay.
So here it's wherever many you collect in the sample. And so we want to test the producer or manufacturer's claim that their percentages are correct. I should zoom out. I need more room to write. Test the company's claim. About their proportions. Why don't we use alpha equals 0.05 level of significance. I already got this shit typed in, I just need to load it up. That is not what I have. Guess we're gonna go off a pure set. And I gotta type it in. Okay, so while you're writing that down, I'm gonna start typing this stuff in. If everyone's done writing, I'll do it in front of you. I'm gonna put up here expected M&M and observed M&M. And we'll call this color. This is 78. 84, 78, 144, 120, 96. I have a dead ringer on green. Oh, look at that, dead ringer on green. A lot of these look pretty close. Brown's fairly close, 78, 83. Yellow's even closer, 84 and 87. Red's kind of close, 78 and 70. It's under 10. Blue and orange are both 14 apart. If there's going to be a problem here, I think it's going to be related to one of those colors. But we'll see. We can say stats. Goodness of fit. Chi-square. My observed value is in observed M&M. My expected value, see, I have two choices. I could tell it where the expected value is, or I can tell it all cells are in equal proportion. I'm going to click compute. Here it gives me my chi-square value. .24 and gives me my p-value, which is 0.515. So we get our information from there. And we'll go back over to StatCrunch and walk through the steps. Oh, hasty. I should have started with my my process. H naught and HA. The observed values match expected. And HA is at least one group is doesn't match expected. All right, so we have our H naught, we have our HA, we have our alpha, we got our p-value and the test statistic from the problem. Process step is what? That's exactly it. What is it? What's the answer here? It's higher, right? 51 cents is definitely higher than 5 cents. So the p-val is not too low. Do not reject the hoe. And do not support HA. That's the one we focus on for our sentence. There is insufficient evidence to show that the Mars company has different percentages for their M&M color distribution. Any questions? All right, let me show you guys another one that has been done by students before. So I'll put it up on the screen while I'm writing on the paper that I scanned. The game Twister has 4 different colors. And a group of students wanted to see if the Twister spinner was fair. To see if the spinner in Twister was fair. So they spun the spinner 350 times. In 350 spins, they had 95 red, 78 green, 88 yellow, and 89 blue. See, at the 0.05 level of significance, test if the spinner is fair. And to do this on some new Dungeons and Dragons dice my friends bought me for my birthday. They are hollow and they have a little dragon inside of them. So it's got like metal frame. They're metal, so I gotta fucking put like a cloth down so I don't fuck up my table. They're metal, but there's a little like metal dragon inside of it, and I don't know that the dragon makes it so that it's weighted correctly where every side comes out equally. So I need to go through. I'm going to do this at some point and roll them and fucking do this goodness of fit test and test to see if they all come up equally, just like they did on this Twister thing. That should be fun. I'm going to, there's 6 different dice, different shapes. I'm going to test each one. All right, so that's the stuff we have. This is the summary of it right here. What we want to do is we test the claim. So on the goodness of fit test, I have 4 groups here, 4 groups, which is in the 3+ category. So this tells me I'm not doing one of like the 2 proportion tests. This has got to be the 3+ category. It tells me it's goodness of fit. That's how you can tell it's a goodness of fit. There's 4 different groups. And so we're gonna say, in this case, what would be if the observed values match the expected values, the twister spinner is fair. Observe, match, expected. HA will be the spinner is unfair. At least one color is off. And I have alpha equals 0.05. I need my p-value. And I need my chi-square value. You guys ready? Nope, I see pins going. Slow your shit down, Jones. I'm gonna start typing up this data in StatCrunch. I got red, I got green, I got yellers, and I got blue. And I will call this column twister. And I will call this twister observe. Red got 95. Green got 78. Yellow got 88. And blue got 89. Now, in the M&M one, we had to calculate expected values because the proportions didn't match. But if the spinner works on the twister thing, red should come up as often as green, as often as yellow, as often as blue. The proportion, there's 4 colors, they should each come up about 1/4 of the time. So we don't need to calculate expected values here. We can just tell StatCrunch to do that shit for us. So that's worth noting here. Same proportions. So we don't need expected value column.
How were they the same proportions? I didn't hear that part.
What?
How are they the same proportions? I didn't hear the part you said before
It's the twister game. There's the colors have the same number of things. If it's fair, they should go up the same number of times. Does that make sense? Like if we look back at the twister picture. Like they should come up the same amount. Each colors has 1 color in each area. It should come up just as often. So we're going to come over here and StatCrunch. I already put them in. I'm going to say stats, goodness of fit, chi-square. Observed is in the twister observed. And all cells are in equal proportion. We click compute. And it determines that the chi-square value is 1.703. And the p-value is 0.6363. So we have what we need from there. We gotta make a judgment call. Is p-value less than alpha? No. P-value is greater than alpha. It's not too low. Do not reject H naught. Do not support HA. HA is that the spinner is unfair. So there is insufficient evidence to support the claim that the spinner in twister is unfair. We can never prove that it is fair. But we can just say there's not enough evidence to show that it is unfair. Do you have any questions?
Why is statistics so like contradictory?
What's contradictory here?
Well, it says like, the spinner is unfair, and then there's insufficient evidence. For the claim that the spinner in twister is unfair.
So it's probably fair. We just can't prove that it's unfair. You want a game to be fair. In statistics, it's all about finding out the truth, or is the situation true, or is there evidence that it might not be true? Very much like in the court of law. Is the person innocent, or is there evidence that they may not be innocent? Is there enough evidence that they're not innocent? Innocent till proven guilty. You got to have enough evidence to show that they're not guilty, or show that they're guilty.
Is chemistry harder than?
I think so. Especially when you, that's just inorganic chemistry. Organic chemistry, I hear, is the fucking, God, I can't say that. It's the take advantage of you without taking you out to dinner first.
I feel bad
Chemistry.
because transfer students have to take all those chemistry classes.
They call it OChem, and I hear students bitching about OChem all the time. I kind of want to take OChem just to see, is it really as hard as they fucking say? Like it's one of those make or break classes for students going down that field.
People warned me about statistics too. Some said it wasn't bad, but I don't
It's
know.
not, it's fucking terrible if you do it by hand. You saw some of the equations that, like I said, like we showed it last week, like, we're not doing that.
Make them work out the entire equation, and I'm like, I wouldn't have made it this far, I'm sorry.
Right?
Exactly.
I don't think it's helpful anyways. You're not gonna do it by hand in real life. No
Are we gonna
employer.
really remember that entire equation after this class is over, especially if we're not majoring in that? and, like,
No.
math or-
But you wouldn't, but looking it up, you could always look it up later on. And if your employer wanted you to do it by hand, you would have the skills to find the formula and know how to use it.
Like, I'm gonna be doing medical math and dosages, I'm not gonna be doing for instance.
Right? Well, there's a lot of statistics in nursing.
Yeah.
Very rarely are you doing the statistics though. What you'll take away from it in nursing is the studies that they're presenting you about the drugs you're giving your patient. Does this sound legit?
There has to be
Or does it sound
research that
shady?
I get.
And this is more along the lines is, is there any biases in their shit? Did they like give good, like, is the setup of how they tested their claim sound reasonable? So like, that's like all the other stuff that goes along with it, not just doing the math of it.
Yeah.
Statistics isn't just the math, it's the whole like. The idea of seeing if something works, that's what they have to do with drugs. Do they statistically work? No drug works for every single patient.
Everyone's like the
Right.
age, their health issues, stuff.
There's all sorts of factors, so something that works for 99% may not work for some. And something that has no side effects for 99% of the people might have a side effect for one of them, side effect for 1%. All right, so that's it for this lecture of GTFO. As far as the whole, yeah, the whole prescription